Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the exergy of thermal energy and its irreversible loss. The exergies of kinetic and potential energies are equal to themselves, and they are entirely available for work. However, the internal energy and the enthalpy of a system are not entirely available for work. For thermal energy, the part by the heat engine that can be converted into mechanical work is called work heat or available energy, and the part of the thermal energy that cannot be converted into mechanical energy is called waste heat or unusable energy. Any thermal energy can be expressed as, in practice, due to the irreversibilities, there is always an irreversible loss, which inevitably leads to a reduction in work heat and an increase in waste heat. Irreversibility can be viewed as the wasted work potential or the last opportunity to do work. It represents the energy that could have been converted to work but was not. The smaller the irreversibility associated with a process, the greater the work that is produced. The performance of a system can be improved by minimizing the irreversibility associated with it. The part of the work heat that is reduced by the irreversibilities in the actual process, or the part that the waste heat increases, is called the irreversible loss of available energy. The natural environments, such as air, lakes, and oceans on the surface of the Earth, have a substantially constant temperature and contains huge thermal energy. However, this thermal energy with the same temperature cannot be used to transform into power, so they are all the waste heat. Firstly, let's find the available energy and the waste heat by a reversible cycle for the thermal energy. A thermal source supplies heat within a certain temperature range as shown by the area, and a working fluid uses this amount of heat to complete a reversible cycle. As shown in Figure 3.15, the heat from the thermal source transfers reversibly to the working fluid. Available energy, the Wmax part of the heat, is converted into work as shown by the area, as shown in Figure 3.15. This is the available energy part of the heat, also called heat exergy. The heat exergy is expressed as, where the variable is an expression of the Carnot cycle thermal efficiency, indicating the relative content of heat exergy in the heat. The remaining part of the heat that cannot be converted into work is waste heat. Venting into the atmosphere, it should be pointed out that the heat exergy is the process property rather than the state one. It represents the available energy part of the heat transferred by the process, not the available energy of working fluid ante-state. For energy, similar to exergy, is also not a state property. Secondly, let's find the available energy and irreversible loss of heat in an irreversible cycle. The existence of the irreversibilities will inevitably reduce the available energy part and increase the waste heat. 1. In the heat transfer process, there is a reduction in available energy and irreversible losses due to the temperature difference. High temperature heat source releasing heat, area under the curve or area under the curve. Low temperature heat source obtaining heat, area under the curve. Can you find the differences of these two amounts of heat? In this case, the available energy is the waste heat is the irreversible loss of available energy is EL1. This loss of available energy is caused by the process of temperature difference heat transfer, and this part of the loss becomes additional waste heat to the environment. 2. Irreversible loss during adiabatic expansion with friction. In this case, the available energy is the waste heat is the irreversible loss of available energy is EL2. The loss of available energy is caused by irreversible adiabatic expansion, and this loss also becomes additional waste heat to the environment. 3. Available energy and irreversibilities during completely reversible process. The irreversibilities in the irreversible cycle include the working fluid has a temperature difference in the heat addition process, a temperature difference in the heat rejection process, friction in the adiabatic expansion process, and friction in the adiabatic compression process. The heat addition to the cycle is the available energy of the heat is the waste heat is the irreversible loss is. All in all, due to the irreversibilities, the part of the provided heat that actually converts to work is reduced from the theoretical maximum value. The reduced part is the irreversible loss of available energy and becomes additional waste heat discharged into the environment. In a completely reversible cycle, due to the limitation of the second law of thermodynamics, there is always a part of waste heat that cannot be converted into work is discharged to the environment, which is essential to complete the cycle. So the waste heat is not an irreversible loss of available energy. Only in an irreversible cycle, the additional waste heat discharged to the environment due to irreversibilities is the irreversible loss of available energy. Thirdly, let's calculate the exergy destruction. Considering that the working fluid in the heat engine returns to its original state after completing a cycle, the entropy remains unchanged. Thus, the entropy change for the isolated system is. Obviously, the exergy destruction is a process quantity, which is for process, not for state, and can be expressed as. Okay, that's all for this task. Thank you very much, and see you next time.